Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So as you know, within this module we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process. And within the second module, now we are going to start a new topic, that is CPU scheduling policy. So in the previous video, we finished with the time sharing topic where we talked about CPU scheduling in great detail. And now in this topic, we are going to start with the scheduling policies. So as we discussed in the previous video about CPU scheduling, it is basically a resource allocation technique where the operating system or the scheduler is trying to allocate the right process on the CPU, right? Or we can look at it the other way around. It is trying to allocate the CPU to different processes, right? So there are limited number of CPUs in any given computer system, and the user launches way more number of programs than the number of CPUs. So to solve this problem, that is to run way more number of processes on limited number of CPUs, we use this technique of CPU scheduling. And in order to select the right process, or we can say the most optimal candidate, the most optimal process for next running on the CPU, we have different algorithms which we call as CPU scheduling policies. That is what we are going to cover in this topic. There are several different types of CPU scheduling policies which optimize for different criteria or different metrics, and that is what we are going to study in this video, in this topic. In this video, I am going to give a brief introduction to all that we are going to cover, the different type of algorithms, right? The different type of computing environments, all of the basic foundation I'm going to lay in this introductory video. So without further ado, let's get started. So let us start the discussion with this slide, right? We have seen this slide in the previous topic also. So basically, we said that in order to understand CPU scheduling, there are several questions or different aspects that we try to understand, right? And to understand these different aspects of CPU scheduling, we'll try to answer these questions. So in the previous topic, we have already answered the first four questions, that is why, how, when, and who, right? And in this topic we are going to focus on the which question. So which question is basically, let me recall all the questions quickly. So the first question, that is why we are doing CPU scheduling, we said that we want to launch way more number of programs on limited number of CPUs. That is why we will, and in order to do that, we will do time sharing. We will share the CPU time among multiple processes, and for that we need to do CPU scheduling. So why we are doing CPU scheduling? Because it allows us to share the CPU time among multiple processes and thus run more number of programs on a limited number of CPUs. So this was the first question, that is why. Then how does this happen? We talked about the mechanisms that exist. So basically, first of all, you have to pause the current process and transfer the control from the current process to the operating system. So here we saw that there are two different ways. One is the cooperative approach, where the process is giving up the control of the CPU on its own. The other is the non-cooperative approach, where we rely on timer interrupts to transfer the control or forcefully take away the control of the CPU from the current process and transfer it to the operating system. Then once the control is transferred, we saw how the context switch happens. That is, switching from one process to another, you have to save some registers and reload the registers of the next process, which constitutes the context switch. So this was about the how question, that is how exactly does this switching happens, right? Then, because at the very core of CPU scheduling is that you're switching the control of the CPU among different processes. So switching among processes is the core thing that we need to be able to do. And how do we do that? We discussed in the previous topic. Then the next question was, when can we do it? So we discussed that there are several opportunities at which the CPU scheduling can happen. Basically, we can switch from one process to another. Some of the examples are like if the process has terminated, or it has given up the control of the CPU on its own because it is waiting, right? Other opportunities are when the process has made a system call, or there has been an exception, or there has been a device interrupt, any kind of interrupt. So in all of these scenarios, the control gets transferred from the process to the operating system. So depending on whether we are only doing the scheduling when the process has given up the control voluntarily, or So that scenario is known as non-preemptive scheduling, right? We discussed this in the previous topic. And if we are doing scheduling at any opportunity that we get, then we can say that kind of scheduling policy is a preemptive scheduling policy. We do not wait for the process to give up the control on of the CPU on their own. So we discussed about preemptive and non-preemptive approaches to scheduling in the when question. That is, when all can we do it? If we can do it at any time, then that is a preemptive solution. If we only do it when the process has given up the control on its own of the CPU, then it is a non-preemptive approach to scheduling. Right. And finally, we talked about who does this scheduling. We talked about the scheduler in detail, like what are the different things that the scheduler does. It maintains several data structures. Basically, the scheduling queues keeps track of which state, like the different states in which the different processes are. And out of those ready processes, it basically keeps track of which process is ready, which is waiting. And out of the ready processes, it makes the selection. So the scheduler is the component, the software component or the module inside the operating system, which is responsible for making the choice. So this was about the different questions and different aspects of CPU scheduling, and we have seen this much in the previous topic. Now, the last question, that is which question, is basically which process should be run next on the CPU. And for answering this question, there are several algorithms, right? So let me show you this with a diagram. So we have seen this diagram in the previous topic also. It basically summarizes the like how we switch from one process to another at a very high level. So if you see, this is the timeline diagram or a Gantt chart where we can see that different processes are executing, right? So this is the CPU and there are multiple processes which are sharing the CPU. And here I am trying to zoom into one of the context switch, right? So as you can see, we are switching from process A to process B, and this is the like part where the context switch is happening. So if we kind of zoom into what exactly happens during a context switch, then at a high level, these are the different activities that are part of the context switch. First of all, you transfer the control to the operating system. We talked about this. Then the scheduler selects the next process that has to be executed. So when you're running process A and now the control is with the operating system, which process should get the control of the CPU next? Will it be process B or some other process? That decision, that choice is made here, right? This is what we are interested in this topic, how this choice is made. We are concerned with the decision making process, right? And once the process has been selected, which will be executed next on the CPU, we make the actual switch, that is which switch from one process to the next process which has just been selected. Here we basically switch the registers, and then once that has happened, we transfer the control to the user process. All of this we have discussed in the previous topic. So let's now focus on this part, that is how does this decision or how is this choice made by the scheduler. So as I said, that the scheduler uses different algorithms which are known as scheduling policies to select the next process. So if you see this diagram, we have a single CPU and there are multiple processes which are ready to run on the CPU. Now the operating system, basically the scheduler inside the operating system, will use some kind of algorithm to select a process from these processes. So now let us see how are these policies designed and what are the goals basically for which these algorithms try to optimize for. Basically, how do these algorithms work? Let's see that. So given a situation like this, that is we have a CPU and there are multiple programs that we want to run on the CPU, which program should we select or should the scheduler select to run on the CPU next? What is the best choice? What is the most optimal process? Well, the answer is it depends. There is no one size fits all. It depends. Let's see what does it depend, right? So if you recall in the first topic of this module, I had drawn analogy between this whole time sharing that we are doing and this DJ. So what is this DJ trying to do? Let's first recall what we are doing in time sharing. In time sharing, there are multiple programs that we are trying to run on a, let's say there is only one CPU, right? There are n programs and we are running it on a single CPU, right? So how we do that? We time share the CPU among the multiple programs. And who is responsible for managing this time sharing? The operating system. So in the very similar manner, in this case, as you can see, there is a music DJ, right? And he's trying to create a music mashup. So what is a mashup? It is a kind of a collection, or you can say he kind of mixing different pieces of music to create something new. And for that he will be running different music in some order, right? He will be switching between different music series, right? So that is the similarity between what we are trying to study, that is the time sharing, and this what this music DJ is trying to do. He has a music player which is very much like our CPU. On this music player, this music CDs will run or play. So these music CDs are like the programs, right? So uh, these are the music CDs, as I said, which are like the programs, and this music DJ is like our operating system. So the music DJ is switching the different music CDs on the music player to create some kind of new music. So let's come back to our question, that is which process, like in this figure we asked the question that what is the optimal selection, that is what is the optimal choice, which process should we run next on the CPU. And as I said, it depends. In a similar manner, you can understand that what is the next music CD that the DJ should play, which one be the best music. It actually depends. It depends on the kind of music he's creating, the kind of audience that he is creating for. Let's say if the audience is in a mood for party, they're youngsters and it's a party kind of environment, then he would select the music accordingly, which has, let's say, high volume, high beats, some music on which you can dance, right? So this is a different kind of music. Compare this with, let's say, the audience is in a mood to relax and they want slow songs, then he will be playing slower songs, right? So as we can see in this, from this example, the best music that or the optimal music that the DJ would select, it actually depends on the audience. What is the audience want to listen? So in the same way, in the computer system also, when we are asking this question is that which process is the best candidate to run on the CPU, it depends on the computing environment, right? Just like in this scenario, it depends on the environment, the kind of the audience, the expectation of the audience depends. The thing that we will optimize for will be different. When we are trying to optimize, like when the DJ is trying to play for a party song, then the criteria would be one that has that the people can dance upon. It should have beats, it should have high volume, those kind of things. And if the DJ is trying to create some kind of music for an audience which is in the mood for slow music, then the criteria to optimize would be slow music, right? Which the audience can relax upon. So the bottom line is that when we are selecting the process, we have to be cognizant or aware of the environment on which we are trying to run. So let me take this figure. So the criteria that the scheduling policy tries to optimize, it actually depends on the goals of the computer system, and the goals of the computer system depends on the environment. So there are different types of computing environments, and each computing environment, so when I say computing environment, consider a smartphone is a computing environment, a desktop is a computing environment. In embedded systems which we see in cars, washing machines, they are also computing environments. But as you can see, all of them are kind of different. So depending on the computing environment, the goals are different. So we'll study about the different types of environments and the goals that are important in each of these kinds of environments. And depending on the goal, the scheduling policy will be designed. So the scheduling policy will be the one which tries to optimize the goals of the current computing environment, right? So another example let me take to explain this point to you. Let's take the example of a city. In a city, there are several citizens, and the government tries to make policies for the people who are living in the city. Now, what policy should be the best for the people of the city? It actually depends. Like depends on the environment. In I have taken two examples. In the first case, let's say we have a situation where there's a healthy environment and a normal life is going on. Then the government can decide to spend, let's say, an equal amount of money on health as well as jobs, right? Employment. But let's say there is a pandemic that we saw recently, there was a COVID pandemic. In such a scenario, we have to optimize for health. So in this environment, the goal is different. The goal is to save the people. The goal is to focus on the health. So the government will allocate more budget to on the healthcare systems, right? The policies would be designed to optimize the healthcare of the overall system. And in this case, the employment can take a hit. Many people lost their jobs in this COVID pandemic. So the government did not want the people to lose their jobs, but the policy has to favor the healthcare system, right? Lockdowns have to be imposed even if people kind of suffer, because the healthcare of the overall system has to be optimized. So depending on the environment, the goals are decided. In a normal environment, the goals are good healthcare as well as good employment. So accordingly, the policies are design. Whereas in a case where is an emergency or a pandemic, here the goals change. The goal is to save the people, and the goal would be to optimize the healthcare. Like, so the policies that would be designed by the government or created by the government in such an environment would be different, right? So this is the point that I wanted to make. Then when we are trying to create a scheduling policy, or when we are talking about scheduling policies, the best scheduling policy depends on what are the goals of the system. And to understand the goals of the system, we have to understand the computing environment. So there are three different kinds of computing environments that we are going to study: batch systems, interactive systems, and real-time systems. So let me quickly talk about what are the different differences between these computing environments, and what are the different goals that are specific to each of these environments. Depending on the environment, the goal will change, and so will be the scheduling policy, right? So let's discuss each of these systems one by one. So now I'm going to talk about the different computing environments one by one, and like talk about the different goals that exist for each of these environment, right? So first of all, let's start with batch systems. So in early days of computing, the computers worked in this way, that is, they were batch systems. In a batch system, what happens basically is that the user submits a batch of jobs, right? And this batch processing computer executes them one by one. So a key feature in batch computing is that it is non-interactive. That is, like what we do today, unlike what we do today, we sit in front of the computer terminal and we expect that we will get a response immediately. That was not the case with batch systems. The programs were written on punch cards, and a collection of punch cards would define a program, right? So the users would submit their program, or you can say jobs, which essentially was a collection of punch cards. And then there was an operator. It That operator like performed the job of the operating system in early days. That operator would take the jobs, basically the collection of punch cards, and put in the batch processing system. So the batch processing computer would execute these jobs one by one. So as I said, the key feature of a batch system is that the usage is non-interactive. You submit a bunch of jobs, and then you can go and do some other work. In the meanwhile, the batch processing system will process or execute these jobs, and then when the results are ready, you can come and collect the results. So this is what used to happen in early days of computing. Nowadays also there are some batch systems. The punch cards are no longer there. We have programs written using some kind of programming language, and then that is compiled to get the binary, right? But still there are batch processing systems in today's world also. So for example, you can see in business scenarios, for example, let's say there is a company, and at the end of the month, the salary of each employee has to be calculated, right? So this is some kind of a processing which does not require a user to sit in front of the computer and wait for it to complete. A user can basically launch a set of jobs which will compute the payroll of the entire company, which could be a time consuming process, right? There could be thousands of employees in that company, and to compute the salary of each of them, the processing would take time. So a batch job can be submitted and it will run, and once it is completed, once the jobs is finished, the user can come and see the results, right? Or there might not be an user there might not even be a user employed. This might be an automated job that runs at the end of every month without user intervention. So this is the nature of batch processing. Some other kind of examples are, let's take the example of banks. In the bank, when you deposit your money, you earn some amount of interest on that deposited money. And the banking system basically works on computers. So the computers would be calculating the amount of interest earned for your money at the end of every month, or whatever is the period of interest accumulation. So periodically these interest calculation jobs, which are essentially a batch of jobs, they'll run and calculate the interest. Here the user did not again interact with the computer while the interest calculation is happening. So as you can see, there are several examples, use cases in business domain where there are a bunch of jobs that need to be executed, and they do not require user intervention. So these are batch systems. One final example is that of scientific applications. So in universities, or even the government can use supercomputers. Wherever there are supercomputers, there the concept of batch jobs still exists. For example, let's say there is the whole data of a population for a country, and the government has to figure out, like, is deciding on some policy. To decide on the policy, it has to get the statistics about the population of the country. So there would be jobs running on supercomputers that will be processing huge amounts of data and calculating the statistics. So this is again an example of a batch system where user does not have to sit. So in this kind of system, in a batch environment, what is the possible goal that would optimize the system? So there are two different criteria that I have listed here. There could be more, but the two important ones are turnaround time and throughput. So turnaround time is the time between the submission of a job and its completion. So ideally, we would want the jobs to finish as soon as possible. So turnaround time is basically the time that the job takes, basically not just execution, but also the waiting time. The entire time that a particular job spends in the system, from the time that the job has been submitted to the time the job has actually completed, this whole duration, this whole lifetime of the particular process, or the batch job, is known as turnaround time. So turnaround time is a concept that we use in our daily lives also. It is basically the time from starting till ending for any particular thing, right? Apart from turnaround time, we want the turnaround time to be small, right? Apart from that, there is this throughput is the number of jobs that are completed in a given period of time. That also we want to be high. Any batch system which is executing a bunch of jobs, it would be a better performance would indicate that we are completing more number of jobs in a given interval of time. So that is what is signified by the throughput. So the number of jobs executed in a given amount of time is known as throughput. And in any batch system, we would ideally like to have a high throughput. So high throughput and low turnaround time. So these are some of the criterias or some of the goals that need to be optimized when thinking of designing scheduling policies for a batch systems. Any scheduling policy that we have to design for batch systems should prioritize the high throughput and low turnaround time in a batch environment. So this was about batch systems. Let's now talk about other kinds of systems. The other major and important type of system are interactive systems, the ones that we use today, right? So in an interactive computer system, the users sit in front of the terminal, as you can see in this image, like what we do with modern computer systems. We operate the computer personally and we expect a good response time. Whatever program that we are running or interacting with, we want a good response time. So in these cases, first of all, let's talk about the examples. So examples of interactive systems are personal computers, laptops, desktops, right? Smartphones, right? All of these are something that the user directly uses. It's not the case like batch systems where user has submitted some jobs or the jobs have been automated and there is no user as such waiting for the job to complete, right? So in this case, in interactive systems, the user is directly interacting, unlike batch systems, and it is the user is expecting a good response time as they are interacting with the programs. They want a good response time. The program should respond or produce output in a timely manner so that they can give more inputs. This is how we use modern day computers or smartphones. We continuously give some inputs and the we continuously receive outputs when the response time is good. So that is the criteria of a good interactive system. It should have a low response time. So that is how we can see the possible goals have been defined. So one is the response time that we talked about. The time from response time can be defined as the time that it takes from the time we submit some input and then when we get the output. This time, like let's say you are a user, you have given some kind of input. The time that it takes to get the output, the time between input and output, we can say as response time. So that has to be minimized in any interactive system. And one other goal is proportionality. So what is proportionality? It is basically users have a kind of inherent idea of how much time a particular task should take. If a particular task is complex, then users are okay with like if the task takes long time. Whereas if a task is simple, then users expect that the time that it takes to complete that simple task should be quick. So you can see proportionality. For example, let's say you copy a big file and it takes a few minutes, you're okay with it. But let's say you're closing a program, that should happen instantly, right? So if that does not happen instantly, then you would be kind of it would be a bad user experience. You would be frustrated, right? So in an interactive system, there is this idea of proportionality, that the amount that it takes for a particular task should be proportional to its complexity. Like long waiting times or long processing times are only acceptable if the task is accordingly or proportionally complex. So these are two of the goals that could be that we should keep in mind when designing any scheduling policy for an interactive system. Any scheduling policy that is deciding which process should be executed next on an interacting system should keep in mind that which process should I execute so that the overall response time of all the jobs in the system is minimized, as well as the proportionality is maintained. And there could be more criteria or goals as well, but these are some of the important ones. Especially response time is the most important criteria, or you can say goals, when we are designing a scheduling policy for a interactive system. So one point that I skipped was that in a case of an interactive system, preemptive algorithms are required. So in preemptive algorithms, basically, as we have studied, the control of the CPU can be forcefully taken away from the currently executing process. If the algorithms that we design, if the scheduling algorithms are non-preemptive, then a particular program could hog over the CPU and not give up the control. Then what would happen is that the other programs that are there in the system, they would not have a good response time. They would not even be responsive. So we do not want a system where one program is only running and the other programs are unresponsive. In an interactive system, when the user is using the system, the user is interacting with multiple programs, and in such a system, it is very crucial, it is essential that whatever algorithm that we define or use should be preemptive in nature. In case of batch systems, right, their non-preemptive algorithms was okay. In that case, a particular job can run for hours and it's fine, because there is no user interacting directly with it. So in case of batch systems, non-preemptive algorithms is acceptable, whereas in case of interactive systems, the algorithms must be preemptive. We should be able to take away the control of the CPU from a given process and be able to assign it to some other process, so that no particular process or program hogs over the CPU, right? So let's talk about the final kind of computing environment, that is real-time systems. So what are these real-time systems? Systems that must respond to inputs within a strict deadline, right? These are special kinds of environments where it is absolutely necessary to respond to the input within a fixed deadline. So some examples, using some examples, we can understand real-time systems. So first example is the airbag safety system in a car, right? So if you see a car, the safety mechanism which releases the airbag when in the event of an accident, it is operated by a computing mechanism, right? It is not manual, it is an automated system. And whenever there is a crash or there is an emergency, basically a crash or accident, the airbag is released automatically, or must be released automatically. So in this case, if you see, the input is that there is a crash or an accident, and the safety mechanism has to respond within a given deadline. It has to respond instantly, right? Otherwise the accident will be fatal and the safety mechanism will be useless, so people will get hurt. So when designing such a system, deadlines are important. Other is the online gaming. So when you're playing an online game, let's say with multiple people, then again here you're expecting the outputs or the response to come within a certain deadline. If it is sluggish, then the online gaming experience will be full of lags and not something which the gamers would be accepting. Again, here the deadline is not as serious or as hard a requirement as the case of a airbag safety system, but nonetheless, in an online gaming environment where there are multiple gamers playing together, they expect that the system should produce the output, or like produce the frames of the game within a certain deadline. Otherwise there will be lag, and that is something that will ruin the gaming experience. And finally, one last example is the air traffic control. In air traffic control, there are several. So basically, this is a mechanism which decides or we can say helps to control the traffic in the airspace. So there are several planes in the airspace, and uh, unlike the traffic lights that we have on the roads, we do not have traffic lights on the air. In the airspace, the traffic is managed by a system which basically ensures that planes are flying in their own zones and they do not collide. So again, air traffic control is something which is receiving inputs in the real time, and it has the information about all the planes in a given airspace. It has to manage all of them and ensure that the planes stay in different zones or apart from each other. Finally, they should not collide. And this is again a deadline based system. If the air traffic control takes a long time to decide the traffic, and by then anything could happen, right? So within a fixed deadline, it has to come up with a proper traffic control, so that planes, when they're flying, they get to fly in their correct zones, right? So this is another example of a real-time systems. So as we saw in these systems, it is important or crucial that the deadlines are met. whatever the inputs are being fed into the system, they are coming at a real time, and the outputs must be produced within a fixed deadline, otherwise there could be issues. So these are the in this case, in the real time system, the criteria or the optimizing goal for any scheduling algorithm is the fact that the overall system should meet the deadline. So when the scheduling algorithm is running on a real time system, the next process that has to run should be the one that kind of ensures that the overall deadlines are not missed. So this is another kind of system. So let's come back to this slide. Here we said that whenever we are designing a scheduling policy, that has to be designed with the goals of the computing system in mind, right? So the scheduling policy, any scheduling policy, when it is running on a computer system, it has to optimize for the goals which are relevant to that computing environment or that computing system. Like no single policy or algorithm can optimize for all the goals, right? So that is why there is no one size fits all. The scheduling policies have to be tailored or designed according to the goals of the system. So accordingly, we talked about three different kinds of computing environments. One is batch systems, interactive systems, and real-time systems. In batch systems, we have a bunch of jobs that are submitted, but there is no user waiting for the response immediately. In interactive systems, we saw that the user is interacting with the system or using the system on a continuous basis, so they want a good response time. And real-time systems are a slightly different kind of system, where the main goal is that when there are once the inputs are coming in real time, and the output or the response should be produced within a given deadline. So depending on these computing environments, we discussed that the goal for each of these environments are different. For batch systems, we want to have high throughput and turnaround, like minimum turnaround time. For interactive systems, the important goals are response time and proportionality. Whereas for real-time systems, it is important to meet deadlines, right? As you can see, in batch systems, we are not concerned about response time. Whereas in interactive systems, we are not concerned about the turnaround time. So different goals have different systems have different goals, and accordingly we can design the scheduling algorithms. The algorithm that will work well on a batch system might not work for an interactive system, right? Obviously it won't be working properly because it is optimizing for a different goal. An algorithm that is designed for a real-time system will not work well for a batch system. So that is the point that I wanted to convey. So we first define the computing environment, then we define the goals, and accordingly we define the scheduling policies. So in this topic, we are not going to look at real-time systems. We are going to look at the more common batch systems and interactive systems in the upcoming videos. We are going to look at what are the different algorithms that optimize for these computing environments. We'll start with the batch systems from the next video. So finally, before I end this video, an important point is that the CPU time is a precious resource, right? All of this that we're doing, it is to optimize a good use of the CPU. The CPU time, it is basically in demand, and it is being it has to be given to all of the different programs that are there in the system. So it is something that we have to use properly. That is why we are designing a good policy, so that all of the processes are the needs of all of the processes are met. The overall system has a good user experience, right? So a good policy can make a difference in the overall performance and the user satisfaction, right? So that is the point that I wanted to emphasize, that it is very crucial, it is very important to have a good scheduling policy, because it will in turn finally define the performance as well as the user satisfaction. So now we are going to talk about the different scheduling policies that are there from the next videos. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.